Well, happy Friday, everyone. My name is Fraser Cain. I'm the publisher of Universe Today, and this is your weekly space hangout for Friday, May 1st, 2015. Happy May Day, I think. So this week we've got news about new photos of Pluto, a progress spacecraft that's spinning out of control. We're going to be talking about water on Mars, sort of, an update on Blue Origin launch, and the end of NASA's Messenger spacecraft. But we've also got a special guest, which is going to be awesome, which I'll get to in 1 second. So, joining us this week, we've got Alessondra Springmann. Hey, Sandy.
Hi, Fraser.
You're still muted, but we've got Morgan Rehnberg. Hey, Morgan. Oh, you're muted too.
Noob mistake. Jeez.
I know. Come on, rookie mistake. All right, and now a mute professional is joining us. We've got Coel Hellier from Keele University, professor of astrophysics. Hey, Coel.
Hi. Hello.
And so, for those of you who don't know, Coel is involved with the SuperWASP project, which is an observatory that is searching for extrasolar planets. So, a big thank you to the Weekly Space Hangout crew for organizing this guest, which came as a complete and total surprise to me, and a happy surprise. So this is great. So before we get on with the actual show, I just want to remind everybody this is an interactive show. You can make any comments, questions. You can suggest some questions to our special guest or to our regular rogue crew here, and we'd be glad to try and answer some of those questions. So just to demonstrate that this is happening, click on the Fraser Cain is interacting live with the audience. Click that, and then you'll still be able to watch the video, but you'll also be able to ask any questions you want. So I'm going to say hi to Sev Dustbunny and Hugo Burnham and Jason Carlson and Stephen Hawkins and Tony Lynch and Patrick Calhoun and Tom Nathy and Peter Waldman and Guido Bibra, Lionel Ward, Nancy Graziano, Ignatiy Romanov, Cherengovsky, Adam Synergy, Graham Ash, Apollo is go. Yeah, so hey everybody, thank you very much for joining us live. We really appreciate it. All right, well let's get on with the sort of the interview portion of the show. We'll take 20 minutes or so and talk to Coel, and then maybe Coel will join us to talk about the roundup of space stories. So Coel, welcome to the Weekly Space Hangout.
Hi, hello.
So for people who have kind of no idea what you do, can you give us just a quick intro?
Okay, so we're searching for planets around stars that are not our sun, so extrasolar planets. The ones that we look for are the ones that transit their star. So that means they orbit in a edge-on orbit such that the planet will pass across the disk of the star, and that will cause a tiny dip in the light of that star, and that means we can detect that presence of that planet.
Right, and so for people who maybe aren't aware of the different methods for finding planets, right? There's the radial velocity where the planet is pulling its star back and forth. There's gravitational microlensing where you get the planet kind of just passes in front of the star when two stars line up, and you get you can detect the planet in that. But in your case, it's the situation where the planet passes right in front of the star, dims it briefly, and then brightens it. So, and it's the same method that Kepler uses, right?
Yes, that's right. Kepler is a space mission. We're doing much the same, but we're looking from the ground.
And I think that's sort of the really interesting thing. So, can you explain the SuperWASP setup? Because it's a very unusual-looking telescope.
Yeah, it's not really a telescope. It's an array of cameras. So really we're using camera lenses, the sort of thing that you can go into a photography shop and buy. And we're sticking high quality CCD cameras on the back of those. And then we take an array of 8 of those cameras, which can cover vast swathes of the sky all at once. And because of that, we can actually look at, say, a million stars all in one go.
Yeah, so I'm gonna share a picture here of the so instrument would be the way you describe it. Yeah, okay, so I can see here you've got kind of eight lenses So are those?
Yep, that's right.
Yeah. So are those like photography lenses? Like I could go down and buy them from
Sure,
Canon or
yeah.
Nikon?
Yeah, they're 200mm camera lenses, so off-the-shelf camera lenses.
Yeah, it sort of looks like a rocket launcher. Um, and then, but then you've got a really high-end CCD on the back. Okay, so you're
That's right.
able to then see a whole bunch of stars all at the same time. So what benefit does that give you as opposed to maybe what Kepler's doing?
Well, that means we can cover much wider areas of the sky than Kepler can do, and that means we can look at a lot brighter stars, because Kepler is roughly 1% of the sky at a time, and therefore there are not that many bright stars in its field of view. We can cover something like 30 times bigger than Kepler, and that means we get a lot more bright stars in our field of view, and that means we can find planets around stars that are fairly bright, and that means they're really good to actually study them in detail and do things like figure out what their atmosphere is made of.
And so how much of the sky are you surveying with this method?
Well, we operate the WASP South that sits in South Africa, and more or less all of the southern sky we're covering. One bit we're not doing is the galactic center. That's just because it's way too crowded for us. But the rest of the sky, other than the galactic center, we're doing.
And so I'm kind of imagining, right? You're taking, like, how long of an exposure would you maybe take? Like, you'd sort of take a long exposure and then move on to another section of the sky. You know, how often are you passing through the same spots of the sky?
Okay, so it'd take 2 exposures, 30 seconds each. So we'd look at a patch of sky for 1 minute, then we'd go on to another patch of sky, and then 10 minutes later we'd come back to the first patch of sky. So we're looking at each patch of sky every 10 minutes, really. And we'll just get as much data as we can on that all night, returning to it every 10 minutes, and then all the next night, and keep going as much as we can.
Right, and I guess depending on where the weather is at and what you can see.
Yes.
So then, so I guess how often then do you come back around and image that same part of the sky?
Well, we'd get we'd be looking at it for 10 minutes, and we'd hope to get as much coverage over the entire season. So a patch of sky we might be able to see for half the year, and we would get as much coverage in that half of the year as we possibly could.
Right, and so then just, you know, the kinds, you know, what kinds of planets are you, you know, like Kepler, it's a space telescope. It's out in space. Yeah. It's away from the atmosphere. It focuses on a very tight region of the sky, I guess very intently, looking at more of the fainter stars. So what kinds of stars and what kinds of planets is your setup capable of finding?
Okay, the ones that we can find are generally the large planets, Jupiter-sized planets, Saturn-sized planets. So, as you say, Kepler is in space, which means it gets much better photometry, so it can look for really tiny Earth-sized planets, and we can't do that because we have the atmosphere in the way. So we can't see the little dips that would be an Earth-size, but we can see Jupiter-sized planets, Saturn-sized planets, and we can find those around bright stars that we can then study those things in a lot of detail.
Right, and so then let's talk about some of the big finds that you've already made, because I know you've already turned up lots of planets, right?
Yeah, over 100 now, and we're still counting. We're aiming towards 200 maybe, but we're well over 100 already.
And so I guess, you know, philosophically, I'd like to know sort of, you know, there's a whole new class of telescopes coming out, like with the 30-meter telescope, which Sandy talked about last week, and things like the Large Synoptic Survey, which are more kind of in a similar kind of class, I think, in that it's trying to survey a big chunk of the sky on a regular basis. So how do you sort of feel about a ground-based approach? You know, what are really the advantages to a ground-based approach as opposed to a space-based approach?
Well, the ground-based approach for finding these transiting exoplanets is simply that we can cover much bigger swathes of the sky than Kepler will do. Now, of course, what you can do is design a space-based mission to also do the whole sky.
Yeah, what if we just took that and put it in space?
And NASA shortly has the TESS mission, which will be the successor to the Kepler mission, and that is aimed to do the whole sky from space.
How many lenses did they stick on that one?
Lots. It's sort of similar to what we're doing, but it'll do it better because it's from space. So that is launch, I think, late 2017.
And so, I mean, I know there was the original the WASP project, and then you upgraded the instrument and sort of went to the SuperWASP. So have you got sort of plans on how to take this technology kind of to the next level? They make bigger lenses, at the Canon store than 200 millimeter. You can probably get a 400 millimeter.
Yeah, that's true. The point is, so if you go to a larger telescope, it looks at a smaller field of view. So then you're competing with the space missions, so which you can't do as well. So actually, our forte is actually the very wide field, looking with wide field lenses and covering more of the sky, because that's what we're good at, and that's what we can really do better than the current space missions.
And so, when you set up the instrument, I know there's sort of like the limits of what you're kind of expecting would be possible. So what is sort of the smallest planet that you've been able to turn up so far?
We've found one just a little smaller than Saturn is the smallest we've got to so far.
And sort of in terms of orbit, you're looking for them to sort of be more in the hot Jupiter class. They're going to orbit their planets a little more quickly than, say, Earth might. Yeah,
that's true. What we're looking for is transits, and of course, the shorter the period, then the more transits they produce, and therefore the much more likely we are to find them. If you take something like Earth, then an Earth-like planet would, of course, only produce one transit a year. And if you say you got to look for, say, 3 transits as a minimum to sort of be sure it's really a transit, then that really requires an awful lot of data. So that is hard. The ones in really, really small orbits, the hot Jupiters, they produce loads and loads and loads of transits, so they're way easier to find.
So one of the sort of downsides of this whole process of searching for planets is the fact that you've really got to get that perfect alignment. You've got to have the planet pass right in front of the parent star to get that dimming. Are there any techniques you think they're going to help us start to discover some of those planets that are maybe off the plane? I know the radial velocity way can kind of get you a bit there.
Yeah, that's true. The radial velocity technique can find planets around any star, regardless of the inclination. But you see, it doesn't matter, you see, because there are loads and loads and loads of stars out there. So all you need to do is look at that fraction of the stars where the planets are aligned. And that gives you plenty to study. So that's why we're looking at a million or so stars, so that we can pick out those rare ones that are edge on planetary systems. But that does give us plenty of these to study.
And based on sort of the amount of time that you've been doing your research, I mean, I know a lot of these kinds of planets, like especially the hot Jupiters, when they were first discovered, they came as a complete and total surprise to astronomers. It was in the, it was in the that's funny classification of scientific discovery. So where has sort of the field of exoplanets come, so far? And how is it sort of like, what big surprises have you all sort of discovered?
Yeah, well, it's amazing, really, because when people started, people would have naively thought, well, all planetary systems will be like our solar system, because that's what all we knew, that's what we were used to. But actually, what we're finding is that all planetary systems that you can conceive actually do exist out there. There's loads of different planetary architectures that are very, very different from our solar system, and essentially any type layout of planetary system that we're sensitive to, we actually find that there are ones like that existing. So more or less, planets can come in any arrays of sizes and distributions.
Right, and I guess what was considered to be impossible just keeps getting found, right? The idea of, I mean, the hot Jupiter, for example, like it wasn't thought that a planet could form, it could be that big and still survive near its star. So, I mean, what kinds of explanations for these strange arrangements do you feel, is most supported? What does your gut tell you right now?
Okay, so the hot Jupiters, they couldn't form where they are. So most of the theorists would say, actually, they formed much further out. They formed much further out where it was colder, and then something has moved them all the way in. And that is probably interactions with third bodies. So you get the Jupiter-sized planet interacting with either other planets or other, maybe if it's a binary star, it will have gravitational perturbations with the other star, and that over long time scales will move it inwards. And that process can move it right into few-day orbits.
So one of the sort of, I know this hasn't been seen yet, but one of the, we're sort of at the very edges of potentially discovering exomoons. This idea of like actually finding moons around other planets. So, you know, what do you think it'll take to actually be able to find some of those?
Well, in principle, we could do it, because if a moon was orbiting around its planet and that planet was transiting the star, then you would see a double or a triple transit. You'd see a transit from the moon as well as a transit of the planet. And that, in principle, could be found already with current technology. And
I guess a situation if maybe you get something that's a little bit more of a binary planet, like what happened with like Pluto and Charon, where you know they're very similarly sized, and I guess if they line up as they go past the star, we might see that dimming in the same way.
Yeah, in principle, if those objects exist, we could find them. What we're most sensitive to, of course, is the hot Jupiters, and it seems that the process that creates hot Jupiters only does it for lone planets. It seems that there are actually few hot Jupiters that have a companion, but if they existed, we would be able to find them.
That'd be kind of amazing. So the one big holy grail in exoplanet search is, of course, the Earth-sized planet orbiting around a sun-like star located within the habitable zone. And although those things have been seen, we've seen lots of sun-like stars, we've seen Earth-sized planets, we've seen stars in the habitable zone, we still haven't seen all three come together yet, really the other Earth. You know, do you think that data exists? I know the SuperWASP can't necessarily pick that up, but do you think that data exists now, like maybe in the Kepler data? Are we about to find that other Earth?
It would be just about possible with Kepler. Although, as you know, Kepler's reaction wheel failed, and that meant it couldn't keep observing the original Kepler field. If it had been able to continue observing the original Kepler field, it might have done that. Because obviously, if you're talking about planets in Earth-like orbits, and you need a lot of data just because the orbit is very long, 1 year. So it's just about possible with Kepler, but it's unlikely. What can do it is a future mission called Plato by the European Space Agency, and that will look at these systems for a lot longer, and that one really can do Earth-like planets in Earth-like orbits around sun-like stars.
Morgan, I know you've got a question.
Yeah, so it's been a point of debate in the astronomical community about whether the Large Synaptic Sky Survey, or LSST, will be able to make any sort of contribution to the search for and characterization of exoplanets. Given your experience in these sort of large sky area surveys, what's your take on that sort of issue?
Well, the LSST is not specifically designed to do exoplanet work. So that would be a sideline for LSST. So it may do some things, but it's not going to be, it's not one of the major things that it's really designed to do well. So the other things like TESS and Plato are actually going to do that a lot better.
It's funny. I've seen, like, when you see the rundown on a lot of the missions, like the Dark Energy Survey and even the James Webb Space Telescope. One of the side things that they're going to do is, and Gaia, is also help find extrasolar planets. So it seems like it's almost like you have to check that off on the features box as you propose your new mission. Yeah,
very much the rage nowadays. Everyone wants to do exoplanets, and if you look at statements of science priorities by NASA and so on, they all say exoplanets.
So I got a question from Adam Synergy. Has the use of robotic, fully automated telescopes been an important factor in the success of WASP and SuperWASP?
Yeah, it has. Our WASP facility sits out there in South Africa. and we do not have a local observer running it. We actually operate it over the internet from England. So most of the time it operates itself robotically and looks after itself, and we just monitor it to see if it goes wrong. Also on some of the follow-up, because we have small telescopes like the TRAPPIST photometric telescope that looks at the objects, the candidates that we find with WASP, and that's also a robotic instrument which you can run from Europe. It's down in Chile, but you can run it from Europe. And that, again, is a much more efficient and cheaper way of running it than sending out an observer all the time.
And how dependable has the telescope been? How often has it broke down on you?
Our WASP South has actually been very reliable. We've been on sky about over 95% of the time. So it's only less than 5% breakdown. Of course, we lose more than that to weather, about 30% to weather. But it's actually been very reliable.
Right, and so I mean that would be great if you wanted to set up, say, on the high plains of Antarctica, for example, where you get a much clearer view. To know that it can be that dependable remotely would be great.
Yeah, that's true. There are people trying to do this work from Antarctica. Of course, you've got all sorts of other issues about doing it from such a cold and environment. But yeah. You also get, of course, 6-month night there.
Yeah. And some of the clearest, driest skies in the world. Tom Nathy asks, have any transiting exoplanets been found around variable stars?
Yes, sort of. Only stars that vary a little bit. If the star varied by a lot, then it would more or less swamp the transit signal. And it would make it very, very hard to actually look for a transit signal if the host star was wandering around all over the place. But if the host star is only varying a little bit, then yes, we have found things like that, yeah.
So we've got a question here that comes from Hugo Burnham, and I actually have no idea what he's talking about. It says, Coel, can you talk a bit about Twinkle?
Twinkle, okay. I know what Twinkle is. It's a proposed mission. What we really want to do with transiting exoplanets is study their atmospheres. And if you look at a planet in the transit, then the planet is in front of the star and is being backlit by the bright star. And that starlight is shining through the planet's atmosphere. And if you compare the spectrum of that in and out of transit and subtract the two, then you get the spectrum of that planet's atmosphere, and that can tell you the composition of that atmosphere. And Twinkle is a proposed mission to look at lots of these transiting exoplanets from space and to try and work out the composition of all of their atmospheres.
Right, okay, and so then by seeing the composition of the atmosphere, you can potentially detect if there's life there, even if there's intelligent life, what kind of cars they drive. Well, that's the that would be the possibility, right? Is what stage in their industrial era they're at.
Well, in principle, yes. If you can find out what exoplanet atmospheres are made of, then in principle you can look for biomarker molecules, things like free oxygen, that you think can only come from life processes. So in principle, that can be done.
I've got one question here from Tom Nathy. Are the cameras independently steerable for fine-tuning on an object, or are they all fixed in place?
The ones on our WASP, they all point the same way, so they're all fixed. Other transit surveys do it differently, where they do have independently pointable telescopes.
This question comes from Nancy Graziano. What is the most distant exoplanet that's been detected to date?
Okay, well, the most distant ones, they're probably one of the ones by the Ogle survey, which look at for microlensing in the galactic, towards the galactic bulge, and they found some really faint things that are probably a large chunk of the way to the galactic center. So they're probably the most distant one.
But of course, you can't confirm them, right? Once those microlensing events go past, you can't go back and take a look at them.
Yeah, that's true. So some of the microlensing events, they tell you about the population of planets, but each event is all that you get about that planet.
So this comes from Lionel Ward. Unlike in our solar system, many solar systems we're finding have gas giants in the habitable zone. How do you rate the chances of life on exomoons around such gas giants? You know, and this is, of course, the forest moon of Endor.
Yeah, I guess in principle it's possible. And what you tend to find is that wherever life is in principle possible, there's a fair bet that life will be there, because it seems that wherever life can exist, then the chances of it happening somewhere is pretty high, even if the chances of it in any particular place is small. So I guess there probably are exomoons with life out there in our galaxy somewhere.
That's awesome. So I think we're sort of reached the end of the time for the interview portion of this. So Coel, I know you you wanted to stick around and maybe talk about some of the space stories this week. So which will be great. So thank you very much though for joining us for that portion. And again, a big thank you to the folks at the WSH crew on Google Plus for organizing the interview. This is just what a treat. Thank you so much.
Okay, you're welcome.
Okay, cool. So let's move on with the big stories this week. So first, let's talk about the end of Messenger. Wah wah. Oh.
So Messenger was launched actually it got inserted into orbit around Mercury 4 years ago yesterday, actually. So it was sort of an appropriate throwback Thursday. So it ended it was launched, when was it launched? It was in August 2004. Wow. And it began orbiting Mercury in March of 2011. And it completed its primary science objectives back in March of 2012, but the mission kept getting extended. It got extended not only once, but twice. And it's mapped the entire surface of Mercury, and it's gotten video of Mercury, images of Mercury, and really helps us understand the planet, its geology, and helped confirm there was actually something discovered actually with radar, that the polar regions of Mercury contained ice and organic material. So it was a really long, wonderful mission. I think a lot of people are really sad. I mean, you'd be sad too if your spacecraft that you'd been working on for probably 2 decades went crashing into a planet. But really, it's the only way to go. And I thought one of the interesting things about the end of Messenger is they'd ran out of fuel, and they were using helium gas that had been used to pressurize the fuel tanks to change its flight path to crash into Mercury.
And I guess in the end they answered the final question: can Mercury be smashed into?
Yes. Though there was a very small chance it would have one more orbit around Mercury before crashing, and so they were listening for it on the Deep Space Network after the crash yesterday.
And I know they took some pictures like right up to the very end.
Yeah, it's pretty sweet. You can see craters. I mean, and the resolution is a little terrifying. You know, how many meters per pixel? You really don't want that unless you're intentionally crashing into a body.
Yeah. So they crashed into the planet at 8,750 miles per hour.
Yeah, if you're following on EYES on the Solar System, which is NASA's simulator for where all the spacecraft are, and with respect to the planet, you can watch it crash. And I think it was fun also that it takes a lot of energy to get closer to the sun. It takes a lot of energy to get to Mercury. And if you look at the orbit that this thing had to take from between launch and 2011, it had to launch from Earth, past Venus, past Mercury, past Mercury again, and then was finally inserted into Mercury orbit in 2011. So it took a lot of work to get there.
But this isn't the end of our observations of Mercury. There's another mission coming pretty shortly. What is it? Bepi Colombo?
Yeah, Bepi Colombo. I believe that's a European. That's an ESA mission.
Yeah.
So hopefully
it'll be arriving in 2017, or it'll be launching, in 2017.
And Coel, how long until we discover other Mercuries?
Well,
around other planets, other stars.
Yeah.
we already have found Mercury-size planets. Kepler has found a couple that are roughly around Mercury-ish sort of size, although those ones are much tighter orbits, much further in than Mercury itself.
Yeah. And then, of course, there's the ones that were discovered around pulsars, which are like even down to Pluto-sized, but that's a whole other kind of planet that you wouldn't want to live on. Not that you want to live on a hot Mercury.
No.
Actually, you could live at the poles. There's water ice on the poles.
Perfect.
You might be bombarded by nasty particles.
From the sun, yeah.
Yeah. I actually had a fellow grad student at MIT who was studying how the solar wind interacts with the surface of Mercury, how the charged particles affect it. And so what she would do is she took a bunch of rocks that we thought were similar to Mercury rocks and would take them to the nuclear reactor at MIT's campus and bombard them with helium. And just see how that would change the surface properties.
And just to confirm that, no, you wouldn't want to live there.
No, I mean, I don't know. I'll take one-way trip.
One-way trip to Mercury.
Yeah, why
Mercury
not?
1 project.
Yeah, send me to Mars, just not with Mars 1.
Yeah.
I find it kind of cool that even though Mercury is the closest planet to the Sun, the poles of Mercury are perhaps the coldest places in the solar system, which is almost mind-boggling to think about. But literally, no light hits the bottom of the craters in the poles, and so there's never anything there to heat them up.
Right, so that's pretty cool. And a number of years ago, they hit the craters with radar, and they said, there are these shiny things in these craters. What could possibly be this shiny in radar? Water ice is that shiny in radar? That's absurd. And then Messenger took images, and there's water ice in those craters to confirm that. So it's pretty cool.
I've just noticed, Sandy, you've got the Arecibo Observatory behind you, sort of in the same way that you used to have the Arecibo Observatory behind you.
Right. Well, it's just a slightly different view. I mean, I've seen that view. Last year, some friends visited, and the telescope was broken, so we couldn't go up to the telescope. But fortunately, one of them had a pilot's license, so we went into town and rented a Cessna 172 and flew over the observatory and took very similar photos to that.
Yeah. All right, let's move on. So, Morgan, there is a Russian cargo ship spiraling out of control.
Oh, it's already out of control. So this was a launch that happened a couple of days ago with the intention of delivering the next load of supplies to the International Space Station. It was the Progress capsule launched aboard or on top of a Soyuz rocket. This is an uncrewed capsule, just to be clear. And pretty much right from the start, things didn't go well. The rocket placed the capsule into its intended orbit, but that was about the last successful thing that happened. Pretty immediately after the capsule deployed, the solar panels opened as expected, but only 2 of the 5 communication antennas were believed to have properly deployed, and that caused a lot of problems with communication with the capsule. Now, alone, that wouldn't have been enough to sort of doom this mission, but they discovered pretty quickly after that 2 sort of automated rocket burns that were designed to fix the orbit of Progress after the launch. And these are normal expected things that happen for every launch. Those burns had not been executed, even though they were programmed into the capsule and didn't rely on communication with these antennas. And so that sort of caused this domino effect where everything just kind of got worse. The orbit wasn't right, and so it started getting less right. And when it was less right, it became harder to communicate. And they finally were able to get a sort of temporary connection with Progress and downlink some pictures to try to figure out what was going on. And they found these sort of very messed up pictures. And they've interpreted this as the spacecraft is in a violent roll. And at that point, they pretty much threw their hands up and said, well, that's that. Because when you have a huge roll, even with a full communications system, it's difficult to maintain a solid connection to upload commands to try to straighten out that roll. In order to do that, you have to download a bunch of telemetry from the spacecraft to try to understand, well, what fuel do the engines have, what speed is the spacecraft moving at, what rotation rate does it have. And if you can't get that information down to Earth, you can't design the appropriate counter maneuver to sort of shore it up. And without that communication that just wasn't possible. And so this spacecraft is sort of slowly starting to dip into denser regions of the Earth's atmosphere, and sometime at least a day from now, but within probably a week or so, it will burn up in the Earth's atmosphere as it falls back. So none of this should hit the ground, but none of these supplies are reaching the space station.
Yeah, this is what they use when they want to take out the garbage on the space station. Is they fill one of these Progress spacecraft with all of their garbage, and then they detach it, and that burns up in the atmosphere, and everything's incinerated. And I guess if they had more time, maybe they could carefully, slowly communicate with the vessel and get it back into a proper spin and try and get it to kind of come back into, maybe try and have it raise its orbit and try for a dock. But in this case, as you say, they've only got a day.
Right, with the combination of slow to impossible communication and extreme spacecraft motion, they just can't compensate for that given the constraints presented. The space station is going to be just fine. The space station keeps on board enough supplies to last even a couple of failed launches before the astronauts would have to abandon the station by returning to Earth aboard the Soyuz capsules that are docked there as lifeboats. But we won't have to wait that long for the next shipment of material, because SpaceX was scheduled to send the next load, I believe, in June. And likely the composition of that shipment will change now that they haven't gotten the supplies from this resupply, but they will be able to top off whatever's perhaps running low on the space station with that commercial launch in June. And this is not the first time this has happened. It's not even the first time in a year that this has happened. You might remember when Orbital Sciences Cygnus blew up on the launch pad last October. That was also slated to deliver material to the International Space Station. And so space is dangerous business. Delivering cargo to the ISS is as routine as anything in space, which means it happens a lot, which means that once in a while it goes wrong. And they're prepared for this, and it'll be corrected.
But, This Week in Musk, this is just another opportunity for SpaceX to demonstrate their Dragon platform and see if that does a better job, maybe, of, it's at a time when dependence on the Russians is already sort of, hanging on by a thread, and this is just another reason potentially to move away from them.
Yeah, there's no quality more important in a rocket than reliability. Everything else is dwarfed by reliability as in importance. So as long as SpaceX can continue to display not only reliability in the sense that missions go off perfectly, but the ability to recover from problems that always will occur. And that happened once, I believe last year, where the Dragon wasn't put properly in orbit, but was able to recover and make the delivery anyway. And as long as you can show that that's a capability you have, people are going to look favorably on you for future space launches.
Yeah, absolutely. All right, let's move on. Sonny, I know you. Did you have another story there? Did I?
I think Morgan's on it. Morgan is just a pile of stories and responsibility
He is. He's a
today.
human story machine. Well, let's move on to the liquid water found on Mars.
Wait, there's liquid water on Mars?
On Mars. Can we go swimming now, Morgan?
Yeah. Can we take Mars One, like the Mars One astronauts, and have like a pool party on Mars? Because that sounds pretty cool.
That does sound pretty cool. Unfortunately, we're not talking about amounts of water that would even be visible to humans, and these aren't. So these are new results from the Mars Science Laboratory, Curiosity, and they don't report a direct detection of liquid water on Mars, but they have very strong supporting evidence to suggest this is probably what's happening. And this sort of shows the value of having long-term measurements on another planet, because what Curiosity has done is measure the temperature at the surface and the humidity at the surface day after day after day, night after night after night, for a couple of years on end now. And by inferring from the patterns of humidity and temperature they detect on the surface, these scientists believe that what's happening is that there is water vapor in the atmosphere of Mars. We're pretty sure about that. It's extremely small amount, but it's there. When nighttime happens, it gets cold, and just like here on Earth, some of that water vapor freezes out and forms as frost on the surface of Mars. And on Earth, when we get frost, it just sits on the grass and waits until morning when it evaporates. But the soil on Mars is extremely salty. And as anyone who's lived anywhere where it snows knows that what's the best way to melt snow? It's to use salt. And so when this frost is deposited on the surface of Mars, it starts interacting with various salts right on that top layer of soil, and that melts the top little bit of the frost. Because what salt does is it lowers the melting temperature. And so with enough salts of the right kinds, you could lower the melting temperature of water so that it melts even at the extreme colds of a Martian night. And then when that water melts, it sinks down just a little bit further into the crust and interacts with even more salts that can sort of keep this melting process going. And so you get sort of, in a sense, liquid water on the surface in the same sort of sense that there's liquid water in the ground underneath the grass in a front lawn here on Earth. It's not flowing around, but it's not in solid form. And then the next morning, when the sun comes up again, temperature's warm, and all of that water evaporates out of the soil and back on into the atmosphere. And because this process happens every single night, the water doesn't stick around in the soil, and so the scientists say this is not a mechanism that could support any sort of microbial life on Mars today or in the past. You need more sustained source of water in order to sustain not only the development of life, but its ongoing existence on the surface.
Yeah, and I guess that was the question that I was going to ask, right? Was like, if you've got that water temporarily in the soil, and then it completely goes away again, any kind of life form would have to be able to survive a few hours of having access to water and then being completely desiccated and then back to water again.
Right, that's absolutely true. I think the real takeaway here is that, once again, another planet looks a lot more like Earth than we previously thought, that there is a water cycle that goes on the surface of Mars, just like there's a water cycle that goes on here on planet Earth. And we know how much water has reshaped the history of the surface of the Earth. It's likely played a similar role on Mars.
I wonder if there are any systems that can help that water get a little deeper. Like here on Earth, like near the poles, for example, you've got permafrost, where you get down to a certain point and the water is fully locked away in the soil, and it's there year-round because it gets so cold in the winter that even in the summertime you dig down a couple of feet and there's your permafrost. I wonder if very similar processes are happening on Mars, that at a certain point down, water is getting held for long periods of time.
Yeah, that's an interesting question because we don't really have the means yet to answer that. We've never drilled or scraped more than a few centimeters into the Martian surface. But that's going to change just in a year or so when the InSight mission launches. And what InSight is designed to do is to drill down into the surface of Mars much farther than have Curiosity or Phoenix or anything like that. And they're looking specifically for thermal changes in the various levels. But you could use that to infer a lot about the structure and makeup of soil underneath the surface. And that would help us really understand if a layer like that could exist underneath.
Yeah. So let's move on to the next story then, Morgan, which is, should we talk about Pluto?
Yeah, let's talk about Pluto, because we're just a few days now away from New Horizons being able to capture images of Pluto that are better, have higher resolution than the Hubble Space Telescope, which made the best maps that we have to this day. But this week they released a pretty striking picture. It was actually an animation taken by the the science camera on New Horizons as part of a navigational program, and it shows Pluto at the center with Charon orbiting around it in a nice clean circle. And that's interesting, but what's more interesting is the variation that you see on what looks like the surface of Pluto. You see very distinct color variations. And this is a black and white image, so we're talking about brightness, white versus dark, on the surface. But as you watch Pluto go around in its rotation, you see distinct changes on the surface.
And the picture here.
Yeah, and Alan Stern commented in a press conference that these changes seem to be much larger in magnitude than on other bodies in the solar system that we've studied. That is, that the difference between the light parts and the dark parts is much more striking than it is when you study, say, Mercury or the Moon or Vesta or something like that. And that bodes well for finding a very interesting surface on Pluto as New Horizons makes a closer approach.
Oh, I think I got the animation here. Hold on. Let's see if this is going to work. Okay, let's try this one. Because it's such a great little animation.
Yeah, it's really beautiful.
No, I don't want to make Internet Explorer my default browser. You even have to ask. Okay, so is that coming through? Okay, so you can see.
We don't see anything right now. We just see your face, your profile picture.
Still?
Yeah.
No. I'm just gonna let it run for a
Fraser,
second.
it's working for me. It looks good. I see it.
Oh,
Yeah,
okay.
I see
Could just
a dark.
be me.
Yeah,
great.
so you can
Looks
see
fabulous. on
this. Yeah, you can
I
see
see it,
like
okay.
some lighter bits, and I'm looking at it on my screen, but you can see some lighter parts and you can see some darker parts, and it really does look like there's some kind of
Right. So what we're looking at
chat going on
here is Pluto in the center, going around with Charon, its largest moon, going around as well. And I think one of the key things to note here is notice that Pluto itself seems to be moving around a little bit. With any other satellite system in the solar system, for example, if you took the Earth and Earth's moon, if you looked at it from this distance, the Earth would appear to be stationary, and the moon would be going around it in a circle. But because Charon is so large in comparison to Pluto, some estimates suggest it's about 10% the size of Pluto, it's actually moving Pluto around just like Pluto moves Charon around. And so sort of the mantra that came out this week was that this is a two-planet system, that if Pluto's a planet, then Charon's a planet too, because it has all the same characteristics that Pluto does in this system.
Yeah, because the point of orbit is outside, the barycenter of their orbit is outside of Pluto, unlike all the other planets. So, Colin, Cole, this is sort of shows some good, I guess, a good example of what we were talking about before, right? We were talking about the potential of a binary planet, and this is a great example of what a binary planet might look like.
Yeah.
And also, I think it also can help people sort of wrap their head around a bit about the way the radial velocity method for discovering planets also works, because you can actually see here, in this case, it's a moon pulling on its planet, but this is how a planet might pull on its star.
Yeah, that's right, because what the radial velocity method does is you don't actually detect a planet directly, because it is too dim to get a spectrum of it, but you can get a spectrum of the star, and the star is moving around through the gravity of the planet in exactly the same way that you can see Pluto moving around from the gravity of its moon going around it. And therefore what you do is you detect the star moving around, the little wobble of it as the planet goes around it, and that tells you that there's a planet there.
Ah, fantastic. That is, and we are just days. We are literally just a couple of days. You said, like, what, about a week now, Morgan, or so, until...
The date I had seen way back when was May 5th. And I don't know if slight orbital changes in the interim have adjusted that, but we're talking about a week, maybe even less, before we'll start to get pictures that are better than the spatial resolution that Hubble has offered us in the past. Now, it could be a little while after that before these pictures are downlinked to the Earth and made available to the public, but we're right on the cusp of discovering this whole new world over the course of the next 2.5 months.
Yeah, just fantastic. Okay, cool. So you had a quick update on Blue Origin.
Right, so we talk a lot about SpaceX, but of course SpaceX is not the only private company working to develop original rocket systems. And another that is also founded by a wealthy Silicon Valley entrepreneur, Amazon.com's Jeff Bezos, is Blue Origin. And so Blue Origin had their first test launch this week of a new system that they're calling, I believe it's New Shepard. Yes, New Shepard is the name of this system. And it's interesting, the launch was successful, and it went up to about 94 kilometers, which is just under the international line of space, set at 100 kilometers, which is about 62 miles. And it was successful all around, but it's interesting to look at how SpaceX and Blue Origin are approaching this the same and approaching it differently. And so we saw that SpaceX immediately went for orbital launches with an intent to develop the capability of delivering cargo and then eventually crew to the International Space Station, as well as launched satellites for Earth orbit. While Blue Origin, on the other hand, is sort of going more in the direction of Virgin Galactic initially. Their capsule is designed to carry humans, although humans weren't aboard during this first test launch, of course, and it's not designed to put them in orbit. It's designed to take them up above the space line of 100 kilometers and return them back to the Earth much in the same way that Virgin Galactic does. And only after developing the technology for that do they intend to move towards technology for actually orbiting their spacecraft. But a way in which they're similar is that both are focusing on landing and reusing their spacecraft, both the rocket and the actual capsule itself. And so I think what we're seeing here is now we've had two new rocket systems developed in the last, say, 10 years. And both of them have focused on the idea of reusing as many of the components as possible. And I think that's a sign that this is the way that the future is going. Even if it takes a while for SpaceX to land on their barge, or even if it takes a while for Blue Origin to successfully complete a similar test of their own, multiple parties are looking at the state of space launch technology and concluding that not only is it technically feasible to reuse these rockets, or at least to attempt to, it's also financially desirable. And I think that's an exciting direction to go, because, and the same thing is true in a sense with Virgin Galactic. They're taking this sort of two-part, fly a plane up to a certain height, then launch your spacecraft from there. But all of these things are looking at reusing their materials as much as possible. And that's the only way that we're going to reduce the cost and therefore lower the barrier of access to space going forward.
And SpaceX has really blazed a trail in getting people accustomed to this being a way of doing it. And so I think for Blue Origin to come sort of kind of to follow in their footsteps and go, we're also making a rocket company, they no longer get, that's crazy. Like that was, SpaceX had to absorb all of the that's crazy, it'll never work people.
Right. I think
and now, Blue Origin gets a bit more of a pass now.
Yeah, I think maybe the most valuable contribution that SpaceX has made to this sort of new era of spaceflight is sort of getting people acclimated to the idea that not everything works the first time. They've failed several times now to land or hover their rocket either above the ocean or on the surface of this barge, and yet people aren't out there trashing SpaceX because they've failed. Now, if NASA had done this and failed and tried again and failed, there would be people out there looking for heads to roll. But with this sort of almost Silicon Valley approach to spaceflight that we're seeing from companies like SpaceX and Blue Origin, the idea of sort of rapid iteration, try this, see if it works, fix it, try it again, see if it works again, tweak it, that's entering the mainstream consciousness as an acceptable way to carry out unmanned spaceflight. You accomplish your primary goal, whether that's launching to the space station or safely delivering a crew to a suborbital flight, but then you make as much use out of the remaining aspects of the mission as you can. And that's really propelling us forward here.
Absolutely. Well, so a big thank you to all of the folks from the WSH crew that submitted stories. We tackled a whole bunch of them this week. I've got one more story, and this comes from Guido Bibra, and that's to let you know that version 1.0 of the Kerbal Space Program is now available. So if you're a Kerbal Space Program player, version 1 is now available, and you can send even more Kerbals to their doom.
And I hear that the Kerbal, they even have female Kerbals now. They're not just male Kerbals.
Oh, good.
Finally.
That was pretty obnoxious.
I'm not going to play until they implement the restricted three-body problem solution. So.
Oh, you're a total stickler.
I am. Girls gotta have standards.
Yeah. I'm waiting for the females. You're waiting for restricted three-body problems. Yeah.
Trojan. Anyway.
Cool. So let's give people. Well, first, I just want to remind everyone. So if you do want to participate in this conversation, go to the WSH Crew community on Google+. Great people there. And they are really the producers of this show. They are the ones who select a lot of the stories that we cover, and they arrange a lot of the guests. So, we're doing a bit of an experiment with this show, trying to sort of push the boundaries of how can we, as the sort of, I guess, the talent, really work with the fans to make the talent. I put a question mark there. The talent to work with the fans to really make the kind of show that you want to see. And so the way that you can do that is get involved in the community. It's a fairly small but very active community and really dedicated. And a lot of the stuff that you're seeing now coming through the show is completely thanks to them. And we wouldn't be able to do it if it wasn't their help. So go to the WSH Crew community on Google+. You can get there. Go to bit.ly/WSH Crew in whatever configuration makes sense to you, and that should work for you as well. Cool. Well, let's give people a chance to sort of tell us more about themselves here. So, Cole, we'll start with you. Where can people find out more about what you're working on?
We have a website. Is there a way I can stick up a URL on here?
You could, but it would take a long time to explain it. So,
right. So,
but I guess people can search for WASP SuperWASP.
wasp-planets.net.
Perfect.
wasp-planets.net.
And if they want to hear specifically from you, are you on some social medias they could follow?
Yeah. Okay. So I'm just at Coel Hellier, also my name, which I can probably stick that up if I can.
And that's just on Twitter. So Coel Hellier on Twitter, and I just followed you. So there we go.
Ah, okay.
I'll hear what you have to say. Sandy, where can people find out more?
Am I muted? No, I'm not. I'm on Twitter. I'm Sandy on Twitter, SONDY. Follow me, and there's snark about planetary missions, and sometimes there's actual science.
Mostly cats.
Are you saying
that?
No,
there's a separate account for cats.
Oh,
please.
Right. Morgan, where do people
find out? That's observatory cats.
You can find me right after the show over at the Google Plus Space community, where I'll take any questions we didn't get a chance to answer. Otherwise, you can follow me on Twitter at Morgan Rehnberg, or visit my website, morganrehnberg.com.
Awesome. Of course, I'm Fraser Cain. Universe Today is my website, and there's my Twitter handle, @fcain. So feel free to follow that. And if you haven't already, please, please, please subscribe. I'm pointing here because usually there's like subscribe buttons in various corners, but it might be, I don't know where it is. But click subscribe to this YouTube channel if you haven't already, and you will get not only this wonderful show that you like, but also the 2 videos that we post every week on the Guide to Space, where I get to talk about snark. Super snarky. So I hope you enjoy those. So thanks, Cole, for joining us this week. We really appreciate you bringing us the latest on exoplanet research.
Welcome.
Really exciting. We are going to find another world, another Earth.
Yes.
Can't wait. All right. Well, thanks, Sandy. Thanks, Morgan, and we'll see you all next week.